about, well, fiber physics. And mostly tied to Higgs boson physics, which is what I'm interested in. So starting with the Large Hadron Collider and below. So outline, basically I'll go through motivation of this physics. I mean, it's been decades since we discovered and started measuring it, so kind of where we're at, what more we can learn. Then I'll focus on the electrification there. I'll give a very quick one slide crash course in that, and then just say what the main take-home message is, at least for collider physics, so we're interested in that. Then kind of look at the specific models just to see, you know, once you go to colliders, it's much more useful to have specific models, because they have something to actually go and search for. So I'll talk about the real scalar singular extension quite a bit, in particular about die-scalar production modes, and this is a little bit of older work and some newer work that's not quite published yet, that areas I think we're missing in kind of searches so far, and especially as it relates to electric transition. And then some caveats about how we think about scalar extensions and simplified models. Then multi-doublet extensions, so 2 HDMs, and then actually some new mechanism for baryogenesis through heavy Higgs decays, and this is kind of the multi-PV range, so we're getting into more future colliders there. And then if there's time, some recent work on CP properties of the top Kikukawa at a muon collider, which is a bit orthogonal to the rest of it, but muon colliders are cool. So there's some really interesting, actually standard model physics that goes on when you get to 10 TeV or 30 TeV muon colliders that has important implications for ESM searches. So if I don't get to that, if you want to hear about that, you can ask. And then conclusions. So where we're at, so this is the most recent update, 2020, and last year, July. This is just Higgs fits. So I mean, so if you're not familiar with this, everything in most of Higgs measurements is through this called signal strengths, where basically we take the experimental value of some initial state producing a Higgs, decaying to the final states, and divided by the standard model. The reason standard model prediction, the reason we could do this is before the Higgs discovered, all we were missing was the Higgs mass. That was the last parameter in the Higgs and the standard model. Once we know the Higgs mass, we can calculate production mechanisms, we can calculate decays, and we can calculate these the higher and higher precisions, because we know everything is completely predicted at this point. So these are just different signal strengths from TMS. The left-hand side are different production modes. The main ones, gluon fusion, some vector boson fusion, things associated with the W. It's not so important with all these different things there. The important thing is they're all lining up with 1, which is the standard model value, and to about some of them to, you know, 10 or 10%. There's all different decay, all different final states. We're going to gamma, 2 photons, 2 Ds, 2 Ws, 2 taus, bottoms, muon, Z gamma. And again, it's not so important, you know, exactly what's going on with all this, except for it's all lining up with 1 pretty well. Again, within about, you know, some of them within 5%, some of them within 10%. Looking very standard model like. And the other thing is on the right-hand side, basically in a standard model, the Higgs boson is the thing that gives all your fermions and your gauge bosons the masses. Okay, so the masses are their coupling times the Higgs Bev, and so the coupling to the Higgs should be proportional to their masses. That's more or less what this is showing. There's the couplings on the y-axis, the mass of these particles on the x-axis. The standard model prediction is a straight line because, as I said, the coupling to the Higgs is completely proportional to the mass because their masses are coming from the Higgs. So you can see going from the top of 173 GeV all the way down to the muon, we're talking about order 100 MeV, 3 orders of magnitude. They're all lining up right on top of the standard model in both the mass and the width, mass and the coupling. So, on one hand, this is impressive that we can actually do this. I never actually thought we'd be having 2 sigma evidence of Higgs to mu at this point. And experiments will always do better than what the knowledge think we can do. But they're much more clever than we are. But you know, this is impressive in that the standard model is working very well. It's also a little depressing in that the standard model is working incredibly well, and this is kind of the simplest thing we could possibly do to give everything masses, and it's working. Okay, but so now what? All precision measurements, they look standard model like. It appears, at least with the observed scalar, I'm going to say observed scalar quite a bit of time because you never know if it's completely the standard model Higgs. It's related to the mass generating mechanism. That's just because that line is straight. The couplings are proportional to the masses, so it looks like it's at least related to it. However, as I said, what actually happens is you have a field, this Higgs, for this phi, what happens is it gets a value throughout all the space called the vacuum expectation value, and the masses from the gauge boson and the fermions are the couplings times the vacuum expectation value. And the part here, that's the thing about this is on the previous slide, we assumed the vacuum expectation value, right? We have not actually determined how the Higgs obtains the vacuum expectation value. We kind of know it has it, we kind of know the coupling proportional to mass, but we don't actually know, we know the value of this guy, but we're not completely sure experimentally how it comes there. So in the standard model, what happens is you just have a bevel that comes from basically the shape of the scalar potential. So you have some potential and you're Gaussian for your scalar, negative mu squared lambda. What happens is the quadratic pulls you down, the quartic pulls you up. You get the minima of this potential someplace else other than zero, and the minima is the vacuum expectation value of the Higgs, so you live down here. So it's the fact that the potential has this shape, you get a vacuum expectation value. In the long run, if I look at this first term is supposed to be an h squared here, is the Higgs mass, and the other ones give me more information about the potential. So the Higgs mass basically just gives me the quadratic piece, the quartic and the trilinear and the quartic pieces will tell me more about the shape down to the minima, and these are the types of things I want to measure. And again, in the standard model, it's completely predictive because in the potential, all I have basically, I have two parameters for the Higgs, I have the mass, I have the vacuum expectation value. I know both of those. I can solve for mu, I can solve for lambda, and then everything else is in terms of those things. That's completely predictive. So in the long run, what you want to do, at least in the standard model, is you want to measure this trilinear. It'd be great to measure this quartic. That is very, very difficult. Trilinear is already hard. So we can do this, and then that will give us a handle basically more on the shape of the potential, where the vacuum expectation value actually coming from. So what we do here, we want to measure the shape. At least in the LHC, you want to do something like this. So you want to measure the trilinear coupling, and the easiest way to do it is apparent production of Higgs bosons, at least directly do it. And so you go through gluon fusion through a top quark, and it's a loop level process. So the top quark has order 1 coupling to the Higgs. So this is a major production mode for the Higgs. And they have a trilinear coupling to go to di-Higgs, and they have another box diagram from the top that contributes as well. And so we want to measure this trilinear, and so search for the Higgs pair production is actually kind of a direct measurement of the shape of the potential. So here I just showed some projection of atlas. They basically have chi squared on the y-axis, and this is the trilinear coupling kappa lambda normalized for the standard model. So one is the standard model, and these are basically these curves are different assumptions that they HLHC on different types of systematic uncertainties and theoretical uncertainties and stuff like that, and how well we can measure it. And the best projection so far is HLHC, and this is from the SNOMAS group. It's about 50% for HH production. There's some indirect couplings as well, because this thing can show up in loops, but it doesn't do quite as well, so combined about 50%. But if I go to future colliders, where I can actually directly produce these things, say a future hadron collider 100 TeV, or a future muon collider, I might be able to get this thing down to order 4%. But this is also probably a more pessimistic number. I think they'll do much better. I think it's so far in the future, we haven't completely focused on getting this thing done yet. And once you combine all the channels, they could probably bring this down by a factor of 2 or so, which would be quite good. Because as I said, the experimentalists are much more clever than phenomenologists. So motivation, what's now? The Higgs is very important. It's the center of electroweak symmetry breaking and gives mass to the standard model. Now we don't know exactly how electroweak symmetry breaking is happening yet, but you might expect deviations basically away from the typical electroweak symmetry breaking mechanism. And if you want to probe the electroweak symmetry breaking mechanism, you want to probe Higgs physics, and that's kind of where it should show up. And it's at the center of many DSM scenarios. You have this thing, electroweak baryogenesis. This creates the matter-antimatter symmetry. Now, this is interesting, and this will be my crash course. And the takeaway of this is that this is interesting because for this to work and get the matter-antimatter symmetry, you have to have physics at the electroweak scale. So a lot of BSM stuff, we can just make the masses heavier and heavier and heavier and decouple it. This is a scenario where we cannot. If there is new physics that actually does this, it has to show up the electroweak scale. If it's at the electroweak scale, we should be able to produce the colliders and go strict for this thing, and might be able to actually, wrap up this scenario, either, discover it or rule out well-motivated models and say a little bit more than saying we're founding Suzy to MTV or something. Higgs portals, this will be in the next slide, and this is just why the Higgs is particularly important. And actually, it's through Higgs portals you can connect it through some dark matter physics. So Higgs portals and scalar extensions, and again, this electric baryogenesis thing is scalar extensions. The reason scalar extensions are particularly important is the Higgs is unique in the Standard Model that at the normalizable level, you cannot forbid this Higgs portal, okay? You can put whatever symmetry you want on the Higgs, you can put whatever symmetry you want on this new scalar. This thing is gauge invariant, and it's invariant under your symmetries. Now, this isn't true of gauge both under fermions, and so scalar extensions are simple extensions that can provide a lot of interesting phenomenology, and they're pretty generic, okay? A lot of BSM, you get new scalars, and then this is there, and it's really hard to get away from it. Now, they can also help solve many problems in particle physics. So, and here, once I have this sort of thing with a new scalar, you have many more scalar trilinear and quartic couplings, not just the Higgs trilinear anymore. I have new trilinears with the new scalars and all these different iterations of that. And there are many new different modes of discalar final states. So I want to try to probe this, because the whole thing is, if I want to understand how the Higgs is getting the vacuum expectation value, I want to understand the shape of the potential. That means I probably actually want to measure as many of these trilinears as I can. And these are through discalar final states, which I'll draw a Feynman diagram in a bit once I have this particular model. And beyond that, and this thing I can't really forbid, and why it's pretty generic, is it's actually interesting that can help solve this electric baryogenesis with the strong first order electric phase transition. So this is the crash course with a lot of words and then the take-home message at the end. So now, if I want to produce the matter-antimatter symmetry of the universe, Sakharov tells us, at least in most models, I want to do three things. Obviously, I want baryons. I have to violate baryon number, otherwise I can't get more baryons than antibaryons. I have to violate it somehow. You need CNCP violation. That basically tells you once you have baryon number violation, well, you actually have processes that can create more baryons and antibaryons. Then you want out of equilibrium interactions, such that when I have a process that creates more baryons and antibaryons, I can't go backwards. Okay, so the process goes forward, but not backwards. Electric baryogenesis is a mechanism that satisfies at least two of these conditions, because the Standard Model doesn't. The Standard Model only has baryon number violation, and this is at very high temperatures in the early universe. You have this. You don't have enough CNCP violation. You don't have out of equilibrium interactions. CNCP violation, I'm not going to comment on, but these out of equilibrium interactions, you want to change the electric phase transition. So what happens in the Standard Model? This is my potential, this is my Higgs, and this is how it evolves in temperature in the early universe. So at very high temperatures, my Higgs actually has 0 BeV. Okay, so everything's massive, it creates a nice plasma. The temperature starts coming down, and at some point I develop a second minimum at the critical temperature, and I'll go from 0 and I'll slowly roll down, and it'll come down 0 temperature, I get a BeV of 246 GeV. Now the thing is, the baryon number violating process of the Standard Model are in thermal equilibrium when you have Higgs out of 0, and then when you get away from Higgs out of equals 0, they go out of thermal equilibrium, and that's where I'm going to get my out of equilibrium interactions, and that's what I want to do. Then I want to change the potential to look something like this, where it's at 0, and I start developing a second barrier, and then what happens if I have that barrier is I'm living here, all these processes, the violated baryon number are in thermal equilibrium, and I tunnel to the second minimum, and I shut them off quickly. That's out of equilibrium interactions. And so I change the shape of the potential to get that to work, and this is called a strong first order electric phase transition. There's various types of constraints you have to have on that. But the whole point is I want to change how my Higgs potential evolves with temperature. I want to change my Higgs potential, and I want to change the Higgs potential at the Higgs scale, and that's the electroweak scale, right? If I set the new physics clear out here, it can't do this, it decouples. So I need something that lives around this scale. And so it becomes a very good benchmark for collider physics because I can't decouple it. So that's the take-home message. So let's look at something. Let's look at simplest extension of the real scalar singlet. So this is the simplest possible thing you can do to the Standard Model, and it actually gives you the phase transition I want. So let's add a real scalar singlet S. And at the normalizable level, you can only enter the scalar potential. So at the normalizable level, it doesn't have couplings to gauge bosons because, well, it's a singlet, so it has no quantum numbers under the Standard Model gauge group. It also turns out you can't write down fermion, gauge-invariant fermion operators because they come in doublets and singlets. And this guy is a singlet, so you can't put it together. And so your potential is something like this. The top line is just the usual Standard Model potential. The bottom line is a term just with the scalar singlets, and the middle term is coupling the Higgs field with the singlet. As this middle term, these are the guys that have to give me have to change how the Higgs is getting the Bev, because if I set these to 0, well, Higgs gets its Bev, the scalar singlet does itself, and doesn't do anything. So these are the terms that do it. Now, what I'm going to stress a lot is this A1 term. This is the thing that gives me the mass mixing, because I replace this phi with H plus Bev, it gives me a bilinear, and if I actually, once I break electric symmetry, I have this Higgs field H and the scalar field S. They're both singlets under the remaining symmetry, and so they can mix quantum mechanically, and then you get mass eigenstates H1, H2, which are admixtures of my original gauge quantum states H and S. And this mixing angle is completely coming from this A1 term. So this mixing angle is proportional to A1, which will be important for some of my motivations for what I want to look for with Collider signature colliders. So H1, I'm always going to assume has a mass of 125 GeV. H2 has a mass M2. I'm going to probably assume it's heavier than H1. It doesn't have to be. Some other people look at when it's lighter, but I'm going to make it heavier, in particular for some hard to reach scenarios. So once we fix the masses, the Vevs, so I'm going to set S equal to 0, which I can do, and the mixing angle just ends up having 3 free parameters, so it ends up being a pretty simple model to kind of play with. It gives you kind of a lot of interesting things. So what's going to happen with this is you want to just work out the phenomenology, so the couplings of the fermions and the gauge bosons. And as I said, this S can't do it, but this phi, so this H does. So everything gets inherited by this H. This couples like the Standard Model Higgs. This doesn't couple, so my 125 GeV guy that I observed has cosine theta times the Standard Model. H2 has sine theta times the Standard Model. I might put my signs around one time. But so the observed Higgs boson, basically it's H1, and it said it's cosine theta times the Standard Model. And it's cosine theta times the Standard Model. So I have a universal suppression to all of my couplings to fermions and gauge bosons. My new guy is sine theta times the Standard Model, sine theta times the Standard Model, which tells me this guy basically operates largely like a Standard Model Higgs at heavier masses. So all the production modes, all the decays, it's operating like a Standard Model Higgs unless you open up something new. So for H1, the rates are universally suppressed. PP to H, you have cosine squared theta times the Standard Model. The branching ratios are unchanged because the widths get universally suppressed by cosine squared theta. Branching ratio is the ratio of widths, so you multiply the numerator and denominator by cosine squared theta and comes up to the Standard Model, which means all these signal things that I talked about, the prediction of this model is the variation, so I divide by the Standard Model. The numerator, the branching ratios cancel. This gives me a cosine squared theta. And all my Higgs fits just put it down on cosine squared theta, independent of mass, which is kind of nice. These are current constraints. These are a bit more than Higgs fits, so the last time I said sometimes you can open up things, let's say above the I Higgs threshold, this heavy guy can decay the I Higgs. So these flat lines here are from Standard Model fits, just the Standard Model Higgs. And of course, you search for these heavy scalars, right? You can produce them, they can decay to various types of final states. And so these are the different types of searches again. But the point is that I don't want to get into all that, but forces my mixing angle to be about less than 0.1 at this point. And they're pretty far constraining. And then these are just different assumptions, but the overall conclusions are about the same. So this mixing still has to be quite small. So what about the electroweak phase transition? So we want to change the Standard Model potential. In this case, it's all coming from the scalar couplings of the potential. So it's A1 and it's A2, which is actually what's coupling my scalar to my field. And after electric symmetry breaking, I actually get many more trilinears. So this is the type of thing I talked about before, but I can have H2 of my trilinears now. And if I want to actually try to map out exactly what's going on with the potential and try to map out what's happening to the phase transition and how the Higgs is getting the Bev, I want to actually search for more scalar production than just di Higgs to map out exactly what's going on everywhere. because I can look at this, I can produce H2, H1, that gives me one trilinear, I produce H2, H2, that gives me a different trilinear, H1, H1, that gives me a different trilinear, and all the different types of discalar final states I can have depend on different combinations of my trilinears. I can try to get information. Now, also, we're already forcing the small mixing angle limit, so what happens with the zero mixing angle limits? So to motivate some things, and I'll go a bit away from the zero mixing angle limit to more current constraints. But at the normalizable level, this is what happens, and this A1, this is giving me my mass mixing term. So if I send the zero mixing to zero, the mixing angle to zero, A1 has to go to zero, and A2 is the only thing that survives. This is the only thing that drives the phase transition. This is the only thing that can change how the Higgs gets the vacuum expectation value. Which means if I want this strong sort of phase transition, if I want to change the way the Higgs is getting the fab, this thing has to be non-zero. And the interesting thing about this is a trilinear coupling of a Higgs to S squared, and so I could have H going to two S's. So something like this. So H1 going to H2, H2, either off shell, which is what I'll focus on, or you could have, if this guy's light enough, you could have on shell decay, which many other people have looked at as well. And part of the thing is the reason you look at this, because especially if this guy is light and this is on shell and this guy is light, those mixing angles are much more constrained, because you would have seen this thing have left a long time ago if you had non-zero mixing angles. So you get really strong constraints there. But that's my motivation, that I want to look for this H2, H2 production, which then I'll relax a little bit. So if I look at all the way I do discalar production, on the top line, so my color coding is blue approaches the coupling approaches the standard model value when the mixing angle goes to zero. Red is when the coupling goes to zero, and green is when the new physics coupling basically doesn't go to zero, so it has to survive to give me my first order phase transition. So the top one is just my usual standard model-like thing. So I'm producing my 225 GeV guy. The first diagram goes to standard model, the last diagram goes to standard model, the middle diagram goes to zero, and so I just get standard model. The middle one is H1, H2. The first one, well, this thing is the same as mixing basically, because I can replace H1 with the BEV, and this becomes proportional mixing angle. H2 coupling to standard model fermions, the less proportional mixing angle, and so the box goes to zero as well. And the bottom one, if I look at the last diagram, 2H2 to standard model fermion, that goes to zero. Just these are the Feynman rules, remember. Middle one goes to zero. First one does not go to zero. Okay, so the production of H2H2 will not necessarily go to zero, because this becomes standard model. And then if this is the only thing that survives, then that's the thing you should search for. So I really want to look at H2H2 first, and then we'll come back to the other production modes and what they can tell us, which is the more newer work. This was done quite a while ago, so this is basically what's called, this is motivation of the nightmare scenario. I could have just tried to make my electric scalar like stable, and it escapes the detector, and I can still get electric phase transition. And then the only way I want to search for it, again, if it's stable, this is the only thing that survives. And the point here is, it's not to go through everything, but there's some of this with the electric phase transition and all these different types of measurements you can do. So trilinear Higgs, vector boson fusion to scalar production 100 CeV. These things also generically shift with the H coupling, and this is future electron positron collider measurements. But the point is, when you put all these things together, you can map out most of the space, and they call this nightmare scenario. And we wanted to see, what if we go a bit away from the nightmare scenario? Because if you go to this thing called nightmare scenario and things are stable, goes out of effect, you have missing energy to tag on, and sometimes, if these things decay, it can actually be much harder to pull it out of backgrounds than if it's actually nightmare scenario. So we will make this slightly not stable, or slightly unstable, and go away from that. So the additional non-resonant modes, and this is just a parameter scan to show what things dominate where. So on the left-hand side, I show for Higgs masses below the di-Higgs threshold, so 240 GeV, you're going down to 170 GeV. The black dots are when I shift the trilinear Higgs by about 30%, because at the time, that's what we thought we could measure the Higgs trilinear to. And so that's when I have my mixing angle pretty big, I can have a pretty big shift. And so if I actually increase it to 50%, it gets worse. The red dots are when the H2 production, so two new scalars, have a larger cross section than H1 plus H2, so Higgs plus new scalar, and that dominates kind of in the middle region. especially in the very small time theta region, which is what I was talking about. And the blue dots are when my standard model plus new scalar dominate my two new scalar. That maps out a lot of this region too. And this is, if I have my mixing angle, a little bit larger, it tells me a lot of information. On the right hand side is now when I'm above the Higgs threshold. So the black one is when actually resonant production, the two Higgses dominates, is the largest cross section. The interesting thing here is even when I go to small mixing angle limits, the resonant production cross section is not the dominant cross section. Okay, yeah.
Can you actually explain this point a little better? What are each of these points representing? Is some like non-curl simulation?
Yeah, so I'm just so the parameters in this model, so there's only three parameters more or less.
Mm-hmm.
So I'm just scanning over what those are with some sort of constraints over theoretical constraints over interpretivity and make sure my global minimum zero temperature actually breaks the electrolytic symmetry correctly and hits balance from below from the potential and stuff. Mm-hmm. So considering those constraints, I'm just scanning over all the possible model parameters in this space. Yeah. And then each one dot is a different one. Yeah. Good. Thanks. But even here in the small mixing angle limits, even though we've all looked at, we think resonances dominate, it doesn't necessarily dominate. I could have a non-resonant production of H2, H2. So different production modes dominate different regions of parameter space. That's good to look for these things. So discalar production and electrolytic phase transition. So just try to get a hold of this again. These are plots again. These are 2D plots, and we're just scanning over what's left over. We fixed the mixing angle, we fixed the masses. So the top one is for mixing angle 0.2, bottom angle is for 0.05, and the left column is for mass 170 GeV, the right column is 240 GeV. And this is just some parameter potential, and the x-axis is actually my coupling between my Higgs and my two new scalars. So it's this coupling that shows up right here. So I just want to see the correlation between that. So and then the white dots are the things that pass all my constraints at zero temperature, my theoretical constraints against perturbativity, dominant from below, correct global minimum. The shaded dots, or the colored dots, are the things that actually give me my strong portfolio electric phase transition that I want to actually live in to get baryogenesis to work. And the point of comparing these two things is actually, I said there's a correlation between this coupling and getting the first order electric phase transition. You can see as I go to smaller mixing angle limits, this thing straightens up, that they start getting a bound lower bound on what this coupling can be to actually give me my first order electric phase transition. So I don't love this. So okay. Yeah, and also it's that I'm working below the resonant double Higgs production, so 170 GeV and 240 GeV, and so I can still actually get electric phase transition because there was an immense amount of work looking at resonant double Higgs production because it's a spectacular signal that I can go look for. It's quieter, you can go look for it, but I can't actually live in these regions to get this thing to work that I want to work, and so I really need to try to map out this entire space and go away from the easy resonant signals and try to look at non-resonant type of things. So we did a Clyde's search for this, or a simulation for this. So we need a holistic approach to search for all possible signals of the extended scalar sector. Resonant double Higgs production provides a great signal. It's been done for a long time, a lot, but there are a lot of regions where Higgs production is not resonant, and we need to consider that as well. And then we focused on this process that I try to motivate. And so this is the thing we looked at first, H2H2. The two masses we're looking at, 170 GeV, 240 GeV. It decays predominantly to W, so it's a 4W final state. And then we do the tri-leptons plus two jets and some missing energy. 14 TeV, we look at 170 GeV and two mixing angles. 100 TeV, then we also did this at 100 TeV. We looked at two masses here at 170, 240 GeV and two mixing angles. The reason we don't do 240 at the current LHC is just because you're trying to produce two scalars with a total, threshold mass at 480 GeV at loop level, and the rates they get very small very quickly as you try to increase the mass. So you just don't quite have the rates on the LHC to get this, but you can actually start doing something with this, as I'll show. So the Clyde searches, this was the HLHC, 300 saddle burns, looking mid-2030s at 170 GeV. The regions that are shaded as yellow is the 2 sigma exclusion, green is a 5 sigma discovery, and then this red dash is when the Higgs trilinear is within 30% of the standard model. That said, this should probably be about 50%, and there's a little bit more of a caveat about this of how much we should trust interpreting this within this model, which we'll try to get to. And the point is here, if I look at these two plots, and it's exactly what I showed before, these direct searches, you do actually start getting into the region of the parameter space that you're interested in with this new channel. And this could be the channel in which, you dominantly produce this guy, especially in small mixing angle, and you could try to discover this type of thing in little bits of this region. And again, this was a fairly simplistic, like cut and count type of exercise, so you could probably update this and do quite a bit better once you use more modern machine learning techniques and deep neural networks and stuff like that. But it's promising. The LHC can do something, which is good. HLHC, you can actually map out most of the space. So this again, yellow is 2 sigma exclusion, green is 5 sigma discovery. And you can see almost except for the scenario with 240 GeV and 170 GeV, you can actually discover most of the region in which I get the electric phase transition that I want in this channel, and higher mixing angles and lower mixing angles. And again, the red dash with Higgs trilinear is within 30%. Here, the red solid, as I said, you generically kind of shift the ZH coupling, and you can measure this thing really well at plus E minus colliders. And so we put that as well as the red. And you can see the collider switches the direct collider switches can actually do better than your precision measurements of E plus E minus colliders in some regions of the parameter space, which is interesting. The other point is that even if you see a shift here first, you see a shift in ZH, you have no idea if it's coming from trilinear coupling. So this is why you want to do direct searches anyway, because the direct searches actually tell you where this physics is coming from. This is, of course, a 30 inverse Hadron, so I will be an old folks home. So other production modes, I said we should look at these for non-zero mixing angles. These can actually be quite important, especially if I push the mixing angle to be 0.2. 0.05 is a little bit harder, but 0.2 works pretty well. H1 goes to the standard model, and this H1H2 goes to 0. In particular, we want to look at this H1H2 because it's something that people don't really look for, this asymmetric production, especially when it's not a resonant production because these masses are too low. And so to increase rates, we looked at 0.2, which is still okay with current constraints. Even if you update these constraints now, we're still okay there. Or you consider 1 mass point. And again, for this mass point, this Higgs dominantly decays into W's. And so we want to look at something like this. And the thing is, if I look at H1 plus H2, this guy predominantly goes to BB bar, so I want to go to BB bar. This goes to WW. The problem with W's is to get a cleaner signal, we like things to go leptonic because we can measure leptons well. At W decays, you lepton and neutrino. You miss the neutrino. You cannot reconstruct this mass very well because this guy is going to 2 leptons plus 2 neutrinos that I'm missing. So trying to reconstruct this mass is very hard. 170 GeV is not actually that far away from 125 GeV. And so trying to separate this from this doesn't work very well, so we put them together. And putting them together actually helps things together. So we actually consider both these processes together in the BP WW final states, and then the W is going leptonically to 2 leptons and 2 neutrinos. This is actually pretty promising. The top one isn't so much. The bottom one does very well. So for larger mixing angles, it can be pretty good. This is HLHC production in the same parameter space again with 3 inverse Hadron. And you can see I get 2 sigma exclusion and then 5 sigma discovery. It looks pretty much like what we had before with what looks at just 2 double scalar productions with new ones. This is Atlas and CMS will each get 3 inverse Hadron. So if I combine them and get 6 inverse Hadron, it turns out that these channels, di-Higgs are usual di-Higgs non-resonant, and H1 plus H2, you could actually map out this entire region for these mixing angles. When you send the mixing angle to 0, it doesn't work as well because it works out, but you could actually map out and discover a lot of this just from the HLHC, which is pretty nice. And then the other thing is the current LHC projections are the Higgs trilinear to within 50%. These dotted lines are, variations of the Higgs trilinear away from the standard model. So one is the standard model, and so you would live between 0.5 and 1.5. And so you can see these direct searches again, you can do better than just kind of measurements of these precision type of measurements, which is useful. This is the newer work. Good. Some caveats. So first of all, the caveat is I kept bringing up these projections of how well I can measure the Higgs trilinear. And the way you talk about measuring Higgs trilinear a lot of the time, at least with these projections, is you take your standard model cross section for di-Higgs, normalize it to the standard model, and look at how the trilinear changes. And so what people usually do is you assume the trilinear changes by itself. So this is our process. So the usual thing when you say you have these bounds is you have these blue dots. So these blue dots are, I don't add this propagator, I fix the top quark count to the standard model value. I only allow the trilinear to measure. Well, of course, the rate depends on one parameter. You have a nice correlation. So if I measure the rate of, to a certain amount, I get a bound on my trilinear coupling. And the left-hand side is a mass for 170 GeV, right-hand side 240 GeV. These are doing the same type of parameter scans as before. The other thing you can do is now the red dots here, I don't include this propagator, I include the first diagram and the last diagram, but now I allow this top quark to vary within the singlet model. And again, with the red, you get a nice correlation. So if I measure the cross section, I have a nice bound. Now, I have a model, I have masses, and I know that quantum mechanically I have to put everything together. I have this middle diagram. Now, I put in this middle diagram, the correlation disappears. Okay, so you have to, that's what I meant by when I said I measure by 50%. It's basically assuming I measure the cross section, I get a bound. So even though, so I have to take those bounds with a little bit of a grain of salt, because once I put the entire thing together, I can see I just destroyed this correlation. And so measurements of the cross sections don't actually give me a direct measurement of the rates as well, of the trilinears as well. So I should just say again, the direct production and trying to search for these things might actually be doing quite a bit better than this. The other word of warning is interpreting results in simplified models. The previous results, you always, when we build simplified models, is we kind of look at, generically what we have, in BSM or complete models, and you assume, well, maybe there's a couple I can produce with LHC energy, and you never actually think that's going to end all be all of everything. So if I go and see a scalar singlets, that's probably not all there's going to be, right? You think, what's the rest of the new physics up there? And you oftentimes assume the new physics is much, much heavier. So basically, you have the standard model, you have a handful of new states, they're below the LHC energy, so you can produce them, and then you have something above the LHC energy. And you can ask, how good is this assumption? Okay, that these things actually decouples, that I can actually ignore what this type of new physics is. And we have a method to just kind of generically do that. And this is effective field theory. I stress this is a normalizable model. I write down everything is normalizable, but I can write down my dimension 5 terms that are non-normalizable. And these operators, I just write them down in terms of standard model fields and whatever my simplified model is and whatever symmetries are. And I can ask, and I can write down what all these operators are. And whatever this new physics is, it will map onto some subset of these operators. It will give this to you. So this thing, basically under basic assumptions, this type of beyond the standard model EFT, it's there when we write down our simplified models. So you can actually just write these things down and see what happens. So we did that as the real singlets we simplified. Oh, yeah. This is from an older time. Yeah. So the EFTs provide a mechanism. And so for the singlet, I can actually just write down what all the next order terms are. What happens with the singlet is now I can have the scalar coupling the two gluons at a direct coupling. It doesn't have to come from the Higgs anymore. I can copy the B's, I can copy the hyperchargers, I can couple the Z's and photons. I can couple to my fermions in dimension 5, so top quark, bottom, tau, muon. And note, even in this electric baryogenesis thing, I talked about the phase transition. I never solved the CNCP violation problem. And one of the popular ways to solve the CNCP violation is you can write down this operator. So even in the electric baryogenesis scenario, you'd expect some sort of new physics here. Of course, this has to be complex, and I'm going to consider everything real to be more simple. But the point is, even in the scenario I'm talking about, you'd expect something else to show up. So you can ask, does this matter? So does it matter? It does quite a bit, because previously all my couplings were inherited from fermions and gauge bosons couplings to the standard model Higgs. But now I have the new operators. I have new couplings to gauge bosons and fermions. And it has direct couplings. So I could look at, how does my 125 GeV guide couple to two vector bosons? This is what I had before, cosine theta times the standard model. but then I have sine theta times EFT. Same with page 2, I have sine theta times the standard model, and I have cosine theta times EFT, and I have to put these things into my searches and my constraints, and the simple interpretations no longer work that well. So we looked at this was a while ago, but this should still hold up because of the way the data works, because of the way it works, So fits and Higgs precision data and direct searches. Left-hand side is Higgs fits, and this is even setting the new physics scale. I assume they're 3 TeV, so I have the Higgs at 100 TeV, and I'm assuming these guys an order of magnitude heavier. I have my delta chi squared. What happened to sine theta? Okay, so if I set all these high order dimensions to 0, and I just do my usual renormalizable model, these are my blue dashed lines. This is why I get a simple interpretation. Only depends on one thing. I just get a bound on sine theta. If I add in these EFT operators, and then these are just different assumptions for consistency. So this is the black and the red dots. I profile over them. I get bounds of sine theta significantly weaker than what I get from just the renormalizable model. This is even with new physics an order of magnitude higher. And stranger things happen when I go look at, when I try to combine my Higgs fits to get it together with, direct search of these scalars that came to W's or T's and stuff like that, 600 G, so this is together 600 GeV. Again, the blue is what I get the normalizable model, and the black is what I get when I add in these EFTs. And the reason you get really strange structures is because when you look at all these measurements for all these bounds and all, WW, D, di Higgs, there's always little fluctuations, and with all these additional couplings, I can fit the fluctuations and change what the bounds are quite a bit. And again, sine theta bounds change quite a bit. There's even some other masses look even stranger. But even new physics pushed up to 3 TeV makes considerable difference. So this is just something to keep back in our mind of how well these things actually be coupled and how far out the new physics is we actually think it is. Okay. So I want to move on to something else. So let me pause. Are there any questions? Yeah.
I guess you discussed like the singlet is like I can replace it by a triplet, right? I can use a triplet Higgs instead of a singlet Higgs for you units or something. Calculate.
Yeah, our singlet, we didn't assume any additional symmetry, so the structure is a little different, but yeah. And you can do it to the Standard Model as well.
And the triplets, when you add, it has some extra implications for this NSI.
Yeah, I think most anything, if you just start to put things into the potential, you can change it.
Just that,
Yes, because you want that barrier, and once you put things into the potential, you can start getting that barrier at tree level. That helps a lot. But multi-Higgs doublets, so you can do this. This is some of the work. I'm going to go over this a little bit quickly. You can do 2 Higgs doublet models, the strong first order electric phase transition as well. And this is just what's supposed to be here is the colored dots are the things that actually get the strong electric phase transition, and then type 1 or type 2 to double model, we won't get into too much. But the point is, the masses really do have to be below 750 GeV. So again, you can produce these things and search for these things with LHC. And these guys did a pretty comprehensive scan of that. So this is looking at just, Higgs resonance production again. The colored dots when I get my electric phase transition, so I can have a hope of getting electric baryogenesis. The red lines are from HLHC searches for resonant Higgs, and you can map out a lot of this region. What's kind of interesting, these guys point out is, sure, I want to look for this thing, because this thing gives me trilinear. But once it's a heavy, I have many other different types of modes I can search for this thing. And the HLHC does very well with this type of thing. So these are way to understand this is, so left-hand side is type 1, right-hand side is type 2. These are things that give me a strong order electric phase transition. And that's the parameters, the total parameter space is the parameter space that passes all the current constraints and gives me strong first order electric phase transition. Each shaded region is for a specific search, so this is H going to 2 Higgs, or measuring my trilinear coupling, and that's the amount of parameter space that this search could eat out of, my viable parameter space. And you can do FF, you could do to fermions, you could do to Z plus H as well, and you can map out a lot of the current parameter space and give me some sort of electric phase transition. And HLHC, about 20% of parameter space will survive for type 1. For type 2, when I put these all things together, about 4%. So HLHC can actually do quite well. And again, this is, future things. This is what we do in the future to map out this entire parameter space. So even though we haven't discovered anything, there are well-motivated models that can give us what we want, and we could actually well-motivated physics scenarios so we can map out a lot of the space. What I want to talk about is something we proposed a while ago. It doesn't feel a while ago. It's in the middle of COVID. I haven't really good at talking about this. So it's baryogenesis from Higgs decay. So the idea here was usually sometimes people talk about heavy lepton decays. I could try to do this where I have a Higgs doublets decaying to leptons. I get an asymmetry of leptons, and then it's in the early universe. So there are processes that convert leptons to baryons. I might try to do that sort of thing. So let's try to do this. Let's try to do this with 2HDM first. So I added second Higgs doublet H2. So I said this HA, and this is the guy that decays. I have my Standard Model Higgs doublet, and I set this in the middle. And so what happens is the baryon asymmetry, it basically depends on the asymmetry parameter of, how often does the heavy doublet go to leptons versus how often does it go to anti-leptons? If it goes to both equally, it goes to 0, I have no asymmetry. So I want to go to leptons instead of anti-leptons more, and I normalize by the total rates, and just squiggly line, you can write it like this, because the entire difference actually comes from the interference of these two diagrams. So the total width just looks like something like 8 pi, and then you have whatever the strongest coupling is squared, then this difference is this interference, so I have a coupling of my H1 to leptons and whatever fermions are inside the loop, and then H2 to leptons, whatever to lepton neutrinos, or whatever fermions are inside the loop. So lambdas are the Yukawas, F are the fermions that dominate the loops, F primes are the fermions that dominate the decays of this H2. And just generically, what I want for baryon asymmetry is 10 to the negative 9. That basically means my asymmetry has to be about larger than that for this thing to work. Now, I need to make sure this asymmetry, as the temperature cools, as the universe cools, it actually persists down to order 100 GeV, where these processes, the violate baryon numbers, shut off. So if H1 is the H1 of the Higgs doublet, it has the mass of the same order, and I can have processes where I have, some doublet fermions go to leptons, and then it goes backwards and goes back and forth, and can just watch this entire thing out. Yeah.
So yeah, which are the leptogens? Are you getting regions from just Faleron processes?
Yeah, exactly. Yeah, we use the Falerons to the variance on this. Yeah, but this thing go back and forth to completely wash this out. So now the problem is, if I try to look at the rate of this thing, okay, so it's a matrix element squared, so it's this coupling squared times this coupling squared. There's only one scale in this process, that's order 100 GeV, so it's D star. Basically, I want the rates of this process to be less than the expansion rates of the universe, so that it can't happen frequently. It expands faster than they can find each other. And this relates to a bound on what these couplings could be, about 10 to the negative 8, it turns out, when we plug in all the numbers order 100 GeV. And if I apply this to the asymmetry parameter, so it looks something like this, but now I know these parameters are less than about 10 to the negative 8. That's order 100, so this entire thing is about less than 10 to the negative 10 times these two couplings. And now that is very hard. You can't actually do that, because basically, to get this to get up to 10 to the negative 9, I need the numerator to be larger than the denominator. But the denominator are the strongest couplings of this guy, so the numerator cannot be bigger than the denominator, and you generically can't get this to work with a 2HDM and this type of scenario. So this is actually why one of these things you want to do 3HDM, so we weren't just getting completely crazy and adding the Higgs. So this is the Higgs troika. You can do that. So you had a third Higgs doublet. So in this case, this can be one Higgs, this can be another Higgs. But now the washout condition, I don't worry about the Standard Model Higgs because it's not inside of these things. It is HA. And if I assume it's heavy, it's completely different, because now it's a matrix element squared again. Now I have the coupling squared of this, the coupling squared of that. But this just becomes 1 over the mass squared, because I assume it's heavier than it's too massive, it's much heavier than temperature. So the numerator denominator becomes mass to the fourth, and then to get the rate right, you have what this is the reheat temperature to the fifth. And so this type of constraint, I put this in. Again, I just assume this guy is order TeV, so it's not very far away. I assume I get up the universe at least gets up to temperatures of over 100 GeV, so I get the salarons and thermal equilibrium. And this upper bound becomes about 10 to the negative 6. And I gain 2 orders of magnitude on the constraints in the Euclides for even TeV scale Higgses. And in that case, I can't actually get this asymmetry constraint to work. So we did this kind of with a specific model. So the full asymmetry parameter, when we do the loop calculation and everything, it ends up being something like this. And then you have some sorts of traces over different types of Euclid matrices. And you assume, and the other thing is we assume that 2 Higgs doublets are close in mass, and not mass. So that this is actually the loop diagram that dominates, because there are other loop diagrams. But if they're close in mass, then you have a resonant production here, more or less. And for the structure of Euclides, which is kind of our freedom here, what I will present is what's so-called this uptight spontaneous flavor violating structure proposed by these guys. Basically, you can get away from a lot of your flavor constraints by these types of assumptions. Is you assume the uptight quark Euclides couple some parameter times the standard model, so that just these things come diagonal at the same time. And then the downside quarks and neutrinos, you assume they're just diagonal matrices. And then we assume the extra Higgs doublets have 0 Vev, which you can always rotate to a basis where your extra Higgs doublets have 0 Vev. And this type of thing can actually evade a lot of the constraints from flavor physics. And they have
the question. So it's true that with the fermions you cannot overcome that constraint at -9. But if I floating the 8 scalar particles in the loop, cannot I overcome that constraint? Because all I do H2, H plus H minus goes to H, and then because now couplings are more free, and then I can use larger value. Because why I have to use the fermion? Anyway,
yeah, we mostly ignore them.
Yeah, because that part can come in and then give you something.
What might happen is, I mean, this thing has to go on shelf.
Right, so
it has to be 2 H1s.
Yeah, but like I use suppose the heavy one, H plus H minus is lighter than those, so those are on my shelf. And then I adjust.
Oh, I see. So you want to get some mass separation.
And then
okay. Yeah, I'd have to think about it because we're doing all of this before electric symmetry breaking when they're all degenerate. Yeah. You'd have to do that after electric symmetry breaking. But then you might have to go directly into baryon stuff, right? Because after electric symmetry breaking, it's Hadron should be out of equilibrium. Yeah. Okay. Yeah, we can talk about it. Yeah. But yeah, this ends up getting away from a lot of the flavor constraints that you always have when you have when you have couplings between scalars and fermions. And they have some sort of UV kind of motivation with this type of thing. But what's actually interesting about this as well is you can actually get S-channel scalar production through quark anti-quark annihilation, which we don't usually think about because the Higgs couples like mass and all the quarks, proton colliders, the initial state quarks are basically massless. They have very small couplings. So this rate is very small, and then it can decay right back into digests. We did look at another different flavor structure that also works because, this is a very generic mechanism. And you can actually do 2HDM to try to do these types of things. But there you end up having to have highly degenerate neutrino masses. You play with loops on the neutrino line at that point and get some resonant enhancement there. And our Higgses don't have to be quite so degenerate. So baryogenesis, these are complicated plots. So on the left-hand side, this is one of those kappas. So this is the diagonal coupling of these heavy guys to the downside quarks. This is the mass of the heavy scalar singlets. This parameter multiplying the Higgs Euclid is about 0.01 on the right-hand side, and the other diagonal elements I set to 0. Right-hand side is just different assumptions of couplings. So assuming all the diagonal pieces are the same, again, the same suppression. So let's see, the dotted lines above are from flavor constraints. All these grayed out areas are things that are not consistent with flavor. So E meson oscillations, K on oscillations, B meson oscillations, that's ruled out. So, and then these shaded regions, so the magenta and the teal, these are the things that actually give baryon symmetry, and these are just two different assumptions of the mass degeneracy. So the mass is within 5% or within 10% to get some sort of enhancement. And from flavor constraints, it doesn't map out a lot of this. We have a lot of region available where you have actually baryon asymmetry from current constraints. And then you try to actually look at what colliders can do. So these are Atlas and CMS projected, just digest constraints projected out to 300 attobarns. You can see right around, 2 TeV, maybe if you get down 1 TeV, they start getting into they start being competitive with the 100 TeV. They don't quite get into what baryon asymmetry is because you actually want these guys to be quite heavy. But 100 TeV, you could actually map out a lot of this. You don't have to go to 30 inverse attobarns. So everything above this 100 TeV is sensitive to, and you could actually, these colliders could map out a lot of this kind of interesting baryon asymmetry producing process. So something in the future to look forward to, far beyond LHC. And again, it's a novel signature that you don't actually usually think of for these scalar decays. So there's 5 minutes, so if you're interested in that, you can ask me. There's interesting afterwards, but I'll just conclude. So summary, the Higgs essential to the story of the electroweak sector, understanding its properties of utmost importance. There are many searches for extended scalar sectors. There's various discalar modes that are sensitive to different trilinears, and non-resonant discalar production can be quite important to close out kind of important regions of parameter space, and a lot of things we're kind of currently doing don't actually get to. Partially is because this is actually really hard to do, whereas the resonant productions are spectacular. So, and searches for many discalar states, resonant and non-resonant, will be needed to try to just fully explore all the possibilities of the electroweak phase transition, electric baryogenesis. We can't just look at just one region of parameter space. Almost all these masses will work. And then we showed a new mechanism to generate the baryon asymmetry through the heavy Higgs decays. You can have Higgs in the multi-TeV range, and it's a novel signature of the Higgs being produced through quark anti-quark annihilation, decaying the digests. I didn't quite get to this, but the muon collider, you have some interesting physics with the CP angle of the Higgs Opti-Tau, and you could tie it down pretty definitively. So anyway, thank you.
You summarize what you're going to say about the wider.
Yeah. The interesting thing is, so this is the cross section. So this is the first I should say, we looked at many different things. So TTH production could do on direct, and then when you get to multi-TeV, these vector boson fusion type of diagrams start taking over and become very dumb because these grow like log of energy, where this decreases with energy. So what happens is they go to very high energy. So this is the cross sections that I can measure for all the TTH type of productions. This is the CP violating angle. I can measure the cross section to about 50%, but then these are the predictions of this cross section with the CP angle at the different energies. So you can see at 30 TeV, I can measure the cross section to 50%. I can bound the angle to about 3 degrees. That's just the standard model has some very fine cancellations. As soon as you do anything with BBF, you have longitudinal vector boson scattering going into something. There's all sorts of perturbative unitarity things. You have all sorts of fine cancellation of the standard model to make sure there's no growth with energy. And then once you shift the couplings a little bit like this does, you get really strong growth with energy, and you don't have to actually measure something that well to get really strong balance. Yeah, it's harder at 3 TeV and 1 TeV, but you could do very well. Yeah, competitive with 100 TeV Hadron collider. Yeah, is that?
Yeah, I was first.
Just about gravitational wave signatures from these sort of phase transitions. How have you looked into the possible observability? I don't know how strong you're going.
I haven't, but I know people look at these singlet models. I think with Lisa, you start getting into the parameter, it just starts getting into it. Yeah. we're actually playing with that a little bit, because this was all the normalizable, and the good thing about non-normalizable, you can add things to your scalar potential, so we're starting to play with that. And see what happens here, so we can open up some more parameter space, and then try that with the gravitational wave, because I know nothing about gravitational waves, I think it's higher, of course.
The question would be, the frequency dependence particular model.
Yeah, right.
And then you can distinguish.
Yeah.
Yeah.
Really to be tough.
Yeah, I think there's a whole lot of degeneracy.
Yeah.
These parameters.
It's just a bit more observable as you.
Yeah, we're kind of earlier, yeah, it'd be nice to, observe it in all these different things, right?
Right.
Yeah, because I think one thing, like, you turn around, like, if you saw something at 5, you could actually try to pinpoint where you're at.
Yeah.
You could have a prediction of what you should see about the phase transition.
Yes.
Yeah, gravitational waves.
What frequency?
Yeah.
Any other question for you? Okay, thank you.